Computer, yeah. Okay, so all right, so hopefully you've read the chapter and watched the video. Let's go through and everybody, I guess, let's say raise your hand if you think the best option is A for this one. All right. Raise your hand if you think the best option is B. Okay, how about C or D? All right, well, what does the X prime, Y prime coordinate mean? Can someone call out what they remember from the reading?
I'm going to change my answer to A, Sean.
All right. That's probably a good choice. Anyone else want to change their answer? Now's the time. Okay, so A is going to be the right answer. So the whole point of the X prime, Y prime coordinate system, as opposed to the original XY coordinate system, is as follows. XY is used to refer to the absolute position, like a fixed object or place. So that's what we were talking about last class. X prime, Y prime is a coordinate system which is kind of tagged to track along a point in the body. So it follows a single point in the body and it doesn't rotate. So that means that compared to the absolute reference frame, maybe anchored to the ground, it won't twist. It just slides, but it follows a point on the body. Okay, so the way we're going to proceed today is basically pick out a point on the body, kind of write down its velocity, and then determine the relative velocities of any other point in the body compared to the, we call it a basis point. Probably a reference point's a better word for it, but anyways, the book says basis point. So, okay. So this point explicitly, this coordinate system does not rotate. That's kind of like its defining property. And if you want to say it does not translate, well, no, the whole point is that it does move with the body without rotation. So in fact, it does translate. The only thing that's true is option A. It's attached to a point in the body. Okay, so now in this relative velocity equation, and when they say relative velocity, what they're saying is the relative velocity of a point in the object relative to the basis point, the X prime, Y prime coordinate system. So B relative to A means any point in the body relative to my X prime, Y prime coordinate system. And your options are A, the relative velocity of B, that's what that would refer to. Option B is it has to be due to rotational motion. C is omega cross the relative vector, or D, all the above. So how many people vote for A? Raise your hand. B, C, or D? Yeah, good. Yeah, they're all, so B and C are just the same thing. They're just different words. And then A, I phrased it so hopefully you got that. So the option is D. Okay, good. So it sounds like people kind of are at least following that notation. Before we get too far into this, I want to go through this picture here. And because I think this sort of describes everything. All right, so that's right. So here's a typical body that we have. And I should say that. Can everyone see the PowerPoint? Is that what's showing? Is PowerPoint showing for everyone?
It is.
Okay, good. All right. So, all right. So here's a typical body, and it can be like a pen. So as it moves around, so in this picture, what they're saying is that if this is a pen here, the top of the pen is moving forward, and the back of the pen is moving in the opposite direction. So the pen is doing something like this. Okay, so the top of the pen is moving forward, and the back of the pen is going the other way. So the kind of absolute velocities of the top and bottom are given in this picture. So you see that the top is moving forward, and the back is kind of moving, the bottom of it, sorry, is moving back and upwards. So the top is moving forward, and the back is, sorry, is moving kind of backwards and upwards. All right. Now, as you guys know, you can decompose vectors however you want. So what they're going to do is write this vector here as the sum of, let me change colors here, as the sum of a vector parallel to, or well, basically the velocity at the top. So I can write that vector as the velocity at the top. So that would be VA plus some other vector. Well, the other vector has to point kind of back and up. So I'm going to change colors again. And then this vector would be sort of like that. And this would be the relative vector in green. It would be V, the velocity of B relative to A. All right. So, B has, the point B has some absolute velocity, that's in yellow. That's relative to somebody watching on the ground, or me sitting in my chair watching this pen move. And what you're saying is, basically, you can think of the motion of B as being two parts. The first part is a translation, so it's just moving along with A rigidly. And then on top of that, so that would be the red vector. And then in green, you would have a rotational component. Okay, and so that's what they're saying in these pictures here. So raise your hand. I apologize for the artwork, but raise your hand if that much makes sense, because that's really the key concept to the whole thing. All right, so that's really that's the thing. So if that makes sense, then you're basically home free. The rest of it's just knowing what a cross product is and working out minus signs and stuff. Oh, get rid of that. All right. Okay, so great. So when you do that, the key point is going to be that remember, so when I wrote the velocity of B as a translation plus a rotation vector is the same for all points. So basically, well, okay, so I can just, whereas the relative vector is going to be only the rotation. So when we had just translations, the relative vectors were zero. The relative velocity vectors were zero. So this part here is the translation part. That's the red vector. And this part here must therefore be the green vector, and it's just a rotation. Okay, so that's the point. And then they just kind of formalize that by saying, oh, okay, the relative vector is a rigid, it's a rotation about the basis point, which in this problem was A. Okay, so that's the thing. So you're really just saying, this is what we, in physics 1, we call this just addition of velocity vectors. Velocity of B was the velocity of A plus the velocity of B relative to A. That's what we did in physics 1. But now they're just saying, oh, okay, we're going to specialize this for a rigid object, and we're going to furthermore kind of mark out and separate translation and rotational motion. And when you do that, then the relative vector is just a rotation. So that's where that formula comes from. So kind of typical problems will be things like this. Okay, you have some sort of a machine, you have an arm that's going to spin. All right, and then you're going to want maybe to figure out a velocity of A, or maybe if you know A, you can work out the velocity of B. Anyways, you can just relate velocities at different points. Oh, why is my, sorry, must be a Zoom feature. What I wanted to say was, when do you use this relative motion analysis? It's really useful. So, and when do you use an absolute position analysis? So what I would say is, if you have well-defined points, then, and you can do the trigonometry and stuff, then maybe you should do the absolute position kind of analysis like we did last class. On the other hand, maybe you don't have good absolute position information. Instead, you kind of have a position of maybe one point on an object, and maybe you only know its velocity or something like that, which is going to be typical in the problems that we have today. Then in that case, you don't want to do an absolute analysis. You want to do a relative motion analysis and do things relative to the one point where you know its velocity. So when you look at a problem and you're trying to decide what you want to do, that's, at this stage, that's how you want to do that. If you know lots of absolute kind of position information, then probably you want to do an absolute analysis. If you know the velocity of a point on a rigid object, then you probably want to do a relative motion analysis, and then you just want to kind of start with the point that you know a lot about, and then kind of leverage that to figure out any other thing you might want. Okay, so here's an example. Times when it's kind of useful. So in this case, you would know, you know that in this arm, that the arm C to B, it's rigid, and it's following, you would maybe know an angular velocity there. So you would know that point B has to follow a circular path. So its velocity has to be tangent to that circle. And since they give you, or they indicate that you might know the angular velocity about point C, then you would know a whole bunch about the velocity of point B. So if you were trying to do a relative motion analysis, what they're indicating, well, either way, you could say then that the velocity of B would be the velocity of A plus the right, okay. So in this problem, so in this picture, what you might imagine doing is trying to figure out what is the angular velocity of the bar from A to B. Okay, that might be a typical problem. So in this case, you would know that A can only move side to side. So that you know a lot about the velocity of A. You know that B can only move along this arc. So you would know a lot about B's velocity. You know a lot about A's velocity. But then you know that they have to be related via a pure rotation. And in this case, I guess the way they wrote it, they're writing it as B rotating relative to A. So they're going to choose A to be the basis point, and you would work out the angular velocity of the rod AB in that way. Okay? So kind of raise your hand if you're following the logic of how that might work. Okay, a few people. Okay. So again, you're going to leverage knowledge of velocities of one or more points to figure out other quantities in this sort of analysis. The other the other type of example that they talk about several times in the chapter and is when you have a point which is not sliding, so it's a fixed point. So as this wheel rotates, the relative velocity of the wheel relative to the ground at this point must be 0 because it's not sliding. And so that then makes it pretty convenient to figure out other quantities, right? So anyway, so you can kind of work out relative quantities. So in this case, let's say you know they give you the velocity of b. So they give you the velocity of b, the center of the wheel, and you know the velocity of a is 0, then you immediately can say that the velocity of b relative to a is omega times r/ab. Well, that's just the radius. So that's, if you can set the velocity of a to 0, that's nothing other than the formula we would have had in physics 1, not written with a cross product, but we would have written it with kind of scalar quantities. Right? So it's just useful when solving problems to know that these contact points, when there's no slipping, they must have 0 absolute velocity, and that kind of can allow you to solve for angular velocities. All right. So those are the types of problems where you'd use this sort of analysis. So hopefully you watched the video. There were 2 examples given. The first one was pretty simple. I thought what we could do is have you guys, let's work through, actually, first of all, were there questions about, no, let's do the group activity first, and then I'll answer questions about the video. So let's go first to the concept quiz. I want you to read that, and then I'm going to ask you to answer those. So first, why don't you go through the concept quiz and try to answer those? I'm going to be right back and ask for your answers. Okay. All right. So you have these options. So if the disk is moving with some velocity 0.0 and they give you omega, determine the velocity of A. So let's see here. Raise your hand if you thought the best option was A. Okay. All right, so yeah, that was the best answer. Somebody who hasn't spoken. Let's see, who can we pick on? Why? Oh, anyways, call out. Why is that the best answer? Why is that the best answer? Jane, why is it the best answer? Why is 0 per second?
I think it's 0 because as it's moving tangentially at 15, point A relative to B, it's not going to be moving translationally, right? It's just going to be down at the bottom.
Yeah. So let's see here. If I do.
Like it would have an angular velocity, but not translational.
That's right. So here we're going to do a demo. Aha. All right. So I want you to watch what happened. Now I need a marker point. dear. All right, I'll just put my finger on the edge. All right, so watch my finger. My finger's right here. Which way is my finger moving, actually?
Your finger's like rotating with the axis.
No, that's just my arm. Yeah, I mean the point of the tip of my finger. Look what happens. As I roll this bottle, my finger doesn't slide. It's not like my finger's sliding. In fact, my finger drops straight down and pulls straight up as I follow it. So there's actually no velocity tangent to the circle. You know, if you watch the whole motion, you might see it, you know, you put a piece of tape or something on the edge of that wheel, you might see it kind of move up or down, but you're not going to see it slide horizontally, at least not at that moment where it's in contact. It moves horizontally, you know, maybe when it's on the top of the circle, but not, and for those of you who are wondering, that is a non-alcoholic bottle because JCC is substance free, and
Yeah, right, Sean.
yeah,
Sparkling water, right?
sparkling. Yeah. Oh shoot! I thought I forgot. This is like my only time to teach like this, so I saved it from the other day. All right. Oh, sorry. So yeah, that was the best answer. 0, because it has no tangential, or has no forward velocity at that point of contact. If the velocity of A is 0, then determine the angular velocity. So can anyone guess? Okay, so what's the first thing you have to do here to pick out an angular velocity? What do you have to specify? Well, you have to pick out minus signs, right? So the way, if I'm going with a standard math definition, the omega that they've indicated, I would call a negative omega, all right? So just be aware of that. With these rotational problems, you always have this tricky business about choosing minus signs. All right, so go through it. How many people got A for their answer? Oh, is it? Okay. How many people got B for the answer? How about C? Yeah. Good deal. You guys got it. So the answer was C. I thought I worked it out. Oh, there it is. Yeah. So, yeah, the answer is C. Basically, you can pretty much do a physics 1 kind of analysis on this because we know that the tangential velocity of an object that as it rotates, it's not really, well, we know that when you have an object that rotates without slipping, the forward kind of absolute velocity here is the same as the tangential speed, if you want, or velocity of a point that follows along on the rim. And that's going to be r omega. So we know that V equals r omega and r is 2. So you're just going to get 7.5 radians per second. Again, depends on your coordinate system. I would have called it negative 7.5, but that's okay. All right. Next up, I want you to talk to the person that you normally sit with. Arnaldo, you can talk to yourself or me. And I'm going to give you the group problem, and I want you guys to kind of chat and talk your way through how you would do this. And this one's a little bit more complicated because you have 2 objects All right. So here are your two objects, and you're told that that omega AB, so that's going to be rod AB, is rotating at 60 radians per second. And we are told that the initial angle theta is 60 degrees, and the initial angle phi is 45 degrees. Now, I'm going to go ahead and maybe hopefully help you here. I'm going to draw in. I went ahead and made, I chose, let me get my colors here. I chose theta. Oh, shoot. Theta. Mouse, draw. I chose theta to be going that way, and I said it was a plus 60. And I chose phi, I chose to measure it positive this way. So it would be plus 45. Okay, so I measured that way, clockwise, so my angles were positive. Now let's think about what's going to happen to this. Can you guys kind of picture what, first, because I know that these rotation problems have all these minus sign things, and you know, if you solve them all the time, then you're confident with your minus signs, you pick your conventions, you just fly through it. But if you don't solve them all the time, you're going to have to, I find it's easier to have confidence in my answer if I kind of think about what's going to happen. So, right, so I need two, okay, there we go. So I'm going to say, I have, here is, oh crap, it's reversed from there. I have to do it backwards. All right, so here is AB, is the short one. Here is BC, the long one. And the end of point C is on the end here. It is only allowed to slide up and down. And AB is going to rotate. So look what happens. Oh, shit. I can't do it. Sorry. It's trickier than it looks. As I rotate AB down, point C can only slide down. And look what it does. It tends to make these kind of scissor and pinch. So phi is actually going to, so basically what I'm saying is that rod phi, phi is going to have to swing down. It's going to have to swing forward. So phi, I'm expecting phi to actually kind of swing and rotate. So I'm expecting rod BC to rotate in a counterclockwise fashion. All right. So just visually, I'm expecting then that I'm expecting omega, it'd be omega BC to be positive. Okay, so as it rotates backwards, so as it rotates, it's going to rotate like that. So I'm expecting that to be phi dot. Basically, I'm expecting to be positive. Okay, so sorry about all that. I'm trying to look at the picture and reverse it. Anyway, okay, so go through and think about how you're going to do this. I'm going to give you guys 3 minutes, and I'm going to ask you about your plans. So talk to your partner, and I'm going to give you guys 3 minutes. All right. So hopefully you guys were able to kind of verbally, and I don't mean run numbers, but just come up with a plan. What is, so that we're going to use a relative motion analysis. To do that, we need to find a point where we know lots about its motion. Point or points, I guess, but really there's one main point. So which point should we make the basis point about which we should build our relative motion analysis? So there are 3 points marked.
Okay.
How many people, how many groups decided to build their analysis around A? Raise your hand.
No.
We
Okay.
built ours around B because we knew that it was going to be needed for the second part, but A is convenient because then you can say that, that VA is going to be 0 because it's stationary. So then you can use that same type of thing to find VB, and that can help you for the next part.
Okay, for the next part. Yeah. So what Shane was saying, I think, is a good way to think of it. This problem, because the motion of B is on a circle, and we know from physics 1 that the velocity tangent to that circle is just r omega, and they give us omega and we give us r. So you could, so we at least know the magnitude of the velocity of B, and you'd have to work out a tangent vector to that circle at that point. So you could just write down the velocity of B. So you could, okay, not right now, buddy. So if you're confident with that, you could just jump right to point B and say that I'm going to use that as my basis point. And then because point C can only move in the y direction, you could do the analysis from there. So you could make B your basis point if you already knew enough to work out its velocity. If not, and actually, well, if not, or if you didn't know that, then what you could actually do is first take A to be a basis point and just say it has 0 velocity. That's easy. Deduce from our relative velocity vector formula the velocity at B. And once you know that, use that as use the output of that first calculation as the input for your next calculation and work out the velocity of C. So how many people just immediately wrote down the velocity of B? Raise your hand if you guys did that. So, okay. A few did. If that's fine. So you guys, if that's how you did it, proceed. If not, then go ahead and start with A, use the relative velocity formula to find the velocity of B, get an answer. Once you have that, use the relative velocity formula to get the velocity of C. Okay, so go ahead, proceed, take another 5 minutes, and then we'll kind of see how far you've proceeded. Yeah.
Rough day, huh?
Yeah. Yeah. Shane, what's up?
Nothing much.
Oh, you have the hand up. I didn't know.
I just forgot to put it down. John, do you think there's any chance that we could maybe go over one of the dynamics homework problems after this first time?
Yeah, we could.
Because there was one, I think it was 16-52. It was like a symbolic one. There's a lot of components to it. It was kind of tough.
Okay. I don't know if I have it written up here, like right with me, but I can look at it and try to figure it out. Or at least give pointers.
I have it open on a screen, so when it comes time, I can just share my screen with you too. So
Okay. All right. How many groups are still making progress? Raise your hand if you're making progress. Nobody. So how about this? Raise your hand if you're stuck. Nobody's stuck or making progress.
I think like me and Nick kind of think we figured it out, but I'm not for sure. So we're not really stuck. We kind of got an answer, but I just don't know if it was the right approach.
All right. All right. So I'm going to switch over to the whiteboard and I'll just work it out there. And then hopefully you guys can see how what I'm doing or what I did compares to what you hopefully tried. Okay, so make sure to put the answer right there. Okay, so we have this problem where we have object C is there, and then I have point B up here, and there's a rod connecting them. So that would be, okay. And they tell me this angle is 45 degrees. And then I have another point here, A, and A is fixed, and I know that the rod from A to B is rotating, and they tell me that this angle is 60 degrees, and I'm going to measure it. I mean, I'm going to measure since they give me a choice, I'm going to measure my angles to be counterclockwise, and then the minus signs of my, if I measure my angles all kind of in a counterclockwise fashion, then the minus signs for quantities match the math notation, so that angular velocities that are counterclockwise will come out positive, and the ones that are clockwise will come out negative. So that's kind of how I try.
So Sean, you said, how do you like tell which point you start from? Like wherever you have more, like, I don't know, more about it?
Okay, so to use the relative motion analysis, you need to have knowledge of one point's velocity at least. So I said in this one, because this point moves on a circle, and we've done lots of circular motion problems. All last year we had lots of physics 1. I could just write down. I would know the speed, I guess, of point B, and then I could use vectors because I know it has to be tangent to the circle, and I could figure it out. I thought though, because I'm not always sure that everybody's really comfortable with cross products and working it out that way. So what I thought I would actually do, even though it's overkill, is start with point A and make that my basis point.
And find the velocity, and then find VC, right? And then.
So first use A, use that to find the velocity of B, and then use the velocity of B to find the velocity of C. Okay. So I thought I would go through it just because that's the long way to do it, and then we kind of get the most practice.
That's why. That's what makes more sense. I don't know if,
But I will just tell you, if you know that it's moving, if we already know that point B has to follow a circle, and you know the radius, and we know omega, and you know then the speed at least is going to be r times omega. So we know the speed at point B, and since it's on a circle, you would just need to find the tangent direction to that circle.
So that's okay.
So, and ultimately, we're just doing that in a roundabout way. But let's do it that way just for practice. Okay. So the first thing I'm going to do, so step one, and again, you could have jumped the step if you kind of saw where everything fit together, is I'm going to say that the velocity of B, this board's flexing a lot, B is the velocity of A plus omega of B relative to A cross R BA. So B slash A. Is that how we're writing it? Are we writing AB? Oh, we're writing it the other way. Sorry. Every book, everybody has their own notation. So, all right. So that's how we're writing it. So watch the labels. I think that matches the textbook. Okay. All right. And we're told, so omega AB.
Sean, what I did was I found RAB as a vector, and we're given omega AB, right? So
That's what I'm going to do. That's exactly what I'm going to do. I'm going to plug in this and this as vectors and do them.
Okay.
Give me a second. Okay. Ken, if you wanted to go upstairs and do TV, but you have to do it yourself. All right. So this is the magnitude of it. And now which way does it point? What vector? So I said it's a vector. What unit vector should I use here on omega AB? Well, it's moving in a counterclockwise fashion. So we're going to call that a positive rotation. This rotation is in the XY plane. So the answer is going to point along my thumb as I curl my fingers with the rotation. So it's going to be out of the plane. It's going to be in the Z direction. Okay, so I'll put a Z hat there. All right, so that's omega AB. Now what about RAB? Well, for RAB, you have to kind of look at it, and I see that, okay, in the X direction, it's going to be, I'm going to use sine of 60, and in the Y direction, I'm going to use cosine of 60.
How do you know they're like negative or positive for the?
If I'm standing here, is it moving to the left or to the right? Well, so point B is to the left, so it's going to be negative in the X direction, but it's vertically upwards, so it's going to be positive in the Y direction. So if you're standing here, because you're finding the position of B relative to A, so if I'm standing at A, I see that it's in the negative X direction and positive Y direction. And I hope I've got my numbers right. So I'm going to write R, change colors here. R, B relative to A, and I have negative 300 sine 60 X hat and then I get plus 300 cosine 60 y hat.
And it's fine if we do them in millimeters.
Oh,
Matter?
you can't. I mean, that's just gonna. We can shift it at the beginning or the end. It doesn't matter.
Okay.
Yeah. All right. If you want, we could make that 0.3 and go from there. This is just what I wrote down in my notes.
Okay.
All right. So raise your hand if you're clear how I got this vector, this relative vector. All right. Okay. Not quite everyone. Mohammed, was that okay?
Yeah.
Okay. And then
Sorry, I forget to raise my hand.
Kirkland, was that okay? Kirkland and Alex, I don't remember if I saw you guys. Yeah, you're okay? All right. Okay. Hopefully that's everybody. So now I just do this cross product. I know that the velocity of A is 0 because that was at a rigid fixed point. It did not rigid, but it's at a fixed point. It's not moving. So therefore I get the velocity of B is going to be 60 radians per second. I'm going to pull those scalars out front, times 300 millimeters. And then the vector stuff I have is going to be z hat cross, and I'm going to get sine 60 x hat with a minus sign plus cosine 60 y hat. All right, and then I remember x cross y is z, y cross z is x, and z cross x is y. Those are the positives, and then if you switch things, you get a minus sign. So I get z cross x is y, so it's going to give me a negative y component. Well, that makes sense because the velocity tangent to the circle should be down in the y direction. And then I have z cross y hat, that's going to give me negative x. So both components in the end of the velocity are going to be negative. So it's going to be down and to the left as I look at it. So that's good. All right, so let's kind of write things out here. All right, so I guess I'll write one more level and then I'll write the answer. So when I write this out, I have 60 times 300 times, and let's see here. So sine of 60 is cosine of 30, so that's going to be 0.866. So we minus 0.866 times z, x is y hat, and then I have minus cosine of 60 is a half, and that'll be x hat. After I do the cross product, that's what I get. When I do z cross x, that gives me y hat, but then there was a minus sign out front, so that's a negative y piece, and I get z cross y is a negative x hat. So I'm going to write this all out. I'm getting negative 1550.90, and it'll be millimeters per second, y hat, minus 9,000 millimeters per second, x hat. Okay, so raise your hand if you got that far. Okay. Well, there's Thomas. Good morning. Thanks for joining us.
Morning.
Did you at least get out of your pajamas today, or you just, no, probably not.
Absolutely not.
Sorry.
Okay, so that's the velocity of B relative, velocity of B. So now that becomes my input. Now I know the velocity of B, so I'm going to rewrite that up on top.
So, Sean, when I did this, I just left the velocity of B as just like a magnitude. I just found the magnitude of it, and I didn't split it up into components. Is that going to screw it up when you find the next part?
Yep. Because you need to do a cross product on the next part. And I mean, I know they have what they call the scalar analysis, but if you look at the analysis, they basically say, blah, 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 use scalars, but ultimately you're going to plug it into the formula for cross product to get the.
Okay. Because I found the magnitude to be 18 meters per second, which works if you do it in meters. And then I just did cosine of 45, but I don't think that's right. Would that end up being? I don't think that would end up being right because I did the VC is going to be that whatever, but we'll see.
Yeah. All right. So I'm going to just write this out. 15.990 millimeters per second. Y hat minus 9,000 millimeters per second. X hat. All right. Okay. So that's, and remember, this is a long way. You might have been able to just write that down from the start with a little bit of just having a mental picture of it. So now the velocity of C. Equals, well, it should be the velocity of B plus the rotation of BC, omega BC, cross R vector from, so the position of C relative to B. Okay, so, well, let's separate out. What are the things that we know? We know the velocity of B, and from the picture and geometry, we maybe don't quite know it yet, but we're going to be able to figure out this relative vector from trigonometry. So these we're going to kind of think of as knowns or easily findable things. We don't know the velocity of C, and we don't know omega. So you might think, well, this is a vector equation. I've got two components. I've got no chance to solve for two vectors because, general vectors, you're going to have multiple pieces of information. However, omega only has one piece of information because these are rotations in a plane. So really, even though I wrote it as a vector, that's really one number. And then the velocity for C, in general, if C was flopping in the air, you wouldn't be able to figure it out. You'd have to have more information. But because it can only move in the y direction, meaning we can set the x component of C's velocity to 0, that's going to simplify things. So really, the only real piece of information, if you're counting scalar pieces of information, is the size, or is omega, the number, the scalar omega, and the y component of velocity for C. So there are two pieces of scalar information, and guess what? This is a two-component equation because it's a vector in 2D. So we have enough equations to solve for whatever we want. But it's useful to go through and make sure that you have enough unknowns to solve for or have enough equations to solve for the unknowns you want. All right, so let's go through how this is going to work. I know this piece. This is what I want to solve for. So what I first need to do is write out what is RCV. Did that over here. Okay, so RCV is invisible. Okay. So C relative to B. Well, okay, so let's go through that. Mohammed, since you asked last time, tell me about minus signs. So RCB, tell me about the sign of the x component and the sign of the y component.
CB?
The position of C relative to B. So if you're standing at B,
To the right.
tell me about the position vector of C. Is it going to have positive or negative x component?
I think for the velocity of VC, for VC, it's going to be negative.
We're not talking about V, we're talking about the position vector, RCB. So RCB just points, it's just a position vector from B to C.
Mhm.
So this vector right here, tell me about its x component. Is it positive or negative?
I would say positive.
Is it moving left or right?
Left.
It's negative.
Oh, sorry. Yeah.
All right. What about the y component?
For the y, I think it's gonna be positive. That's
Is this vector moving up or down?
hold on. Down.
To C, it's going down, so it's got to be negative.
It's hard to see. That's what's getting me all the time.
All right. So
Nice.
RCB means if you're standing at B, looking at C, which way would that vector point? So if you're standing at B, looking at C, RCB points that way.
Mhm.
So this would be,
Oh, okay. So down and left. Okay.
yeah. Okay. So I'm expecting negative, negative. So now I'm just going to mathematize it. I know that the size of that vector is 600 millimeters. Okay, that was in the problem. So this distance is 600 millimeters. And so that's just going to give me some red. So it's going to be negative 600. I'll write it as sine phi, which is just 45. So strictly speaking, that should give me the x component using sine. It doesn't matter because it's 45 degrees, but just to be consistent. And then I'm going to get minus 600 cosine 45 in the y direction. The board's bouncing around on them. Okay, so that's this guy. I don't know omega, but I do know the way I defined my angles. I mean, I can just think of omega as being some number times z. So I can say omega BC is just some number, omega BC times z hat, and someone else. Who haven't I picked on? I don't know. How about we'll do it this way? No, so there's no pressure. Think about what's going to happen to this thing as it rotates. Okay. As it rotates, so which way is this thing rotating? So visually, think about how it's rotating, and then raise your hand if you think that this omega number is going to be positive, and then I'll ask about negative. How many people think omega should be positive? Raise your hand.
Sean, does that say omega B C Z hat?
Yes. The vector
So,
points out of the plane. So this is the scalar angular velocity. This is the vector quantity. It points along the axis of rotation. All right, so those people think it's positive. How many people think it's negative? I'm not getting any takers on that. Yeah. So if you think about it, this is going to rotate down. It's kind of like C is moving faster than B. And that means that omega is going to be generally in the counterclockwise orientation. So that I'm expecting, if I do my minus signs correctly, this thing will be positive, right? So if you work really hard on understanding the positive and negative angles, then that can help you have confidence. Because if I get this thing to come out the right way, then I'm pretty sure I haven't fouled it up. Because I know that minus signs are the hardest part of any of this. All right. So now I just write this all out. Let's do omega BC cross RCB. So that's going to have a z hat cross x hat. Z hat cross x hat is positive y hat. So I'm going to get, but then I've got a minus sign up front. So I'm going to get a negative answer in the y direction. That's good because I expect the thing to move down. And then I'm going to get z hat cross y hat. Z hat cross y hat is negative x hat, but I have a minus sign out front, so that's going to give me a plus sign for the x component. I've done that right, so hopefully I didn't screw that up. No, hold on. So I fouled it up. I'm worried that I fouled up my minus signs. Oh, no, I got it right. It's a miracle. Okay. All right, so when I do that, that's going to give me, so the magnitude, the scalar for omega comes out front. And then I'm going to pull out a common factor of 600 millimeters times, and I'm going to get a z hat cross x hat times sine 45. That's going to be double negative. I'm going to get plus z hat cross x hat is y hat. So minus sine 45 y hat. And then I'm going to get positive, it should be cosine 45 x hat. And I know sine 45 equals cosine 45, but then you can kind of see where it's coming from when you work out the cross product. All right. Raise your hand if you do omega cross r and you get that answer. Raise your hand if you follow that.
Sean, so my question is, so when you're leaving omega of BC arbitrary, does that just mean that you're not going to need it in the end? Like you don't need the actual value? Or
We will need it. We will need it.
you can relate like the omega from AB to that using something else, or?
So we're going to have to solve for it.
Oh, I see.
So if I knew it already, I would just add the vectors. I would be done. If I knew it already, I would just do an absolute motion analysis and just write my answer down.
Gotcha.
And I can't. All right, so we're running short on time. So hopefully you see that, where that comes from, and then I'm going to write out how to solve it then. Okay. So I know, so I have VC, I'm going to just plug everything into this equation. VC, I'm trying to find, but I know it only points in the y direction, and it should be negative. This gives me, writing it all down, yeah, all right, I'll write this out. This first term gives me negative 15,590 y hat from here. And then I get minus 9,000 x hat. That came from VB. And then the second term gives me plus and plus what I just wrote down, which is going to be omega times 600 times, and I'm going to have, so zx gives y, so I get minus 0.707 y hat plus 0.707 x hat. So I've just plugged in what we had before, and I've typed in sine of 45. Well, typed in, I just do it. Okay, now to add them together, I'm going to regroup. So I can write this as, and then I have x hat. So the x hat piece is going to be this and this. So that's going to give me minus 9,000 plus omega times 600 times 0.707 bracket, and then I get plus y hat times negative 1590 minus 600 minus omega times 600 times 0.707. Sorry, I'm going fast here. So what I've done is I just I wrote this formula out. We found all the pieces. I just plugged it in and I regrouped X and Y. Raise your hand if you kind of see where I'm getting these little bits. Good, good. Yeah, okay. So now what I'm going to do, Shane, to answer your question about omega, I know that the X component of C's velocity has to be 0.
So you set it equals 0, solve for omega, and then plug it back in for the y component?
That's it. And that trick gets used over and over.
Okay.
Whenever you have an object that's sliding, you can use that fact to set one of the components of velocity 0, and you solve for something that's unknown. So when I do all that,
Wait, what are we setting 0 again? What did he say?
so the slider, the C can only move in the Y direction.
Oh, okay.
So the X component must be 0.
Is
That
there?
means all this X stuff is 0.
Mhm. All right.
And shoot, I had the numbers all written out. Oh, there it is. I've got it. All right, good. All right, so write the answers down. And then, okay. So for omega, I find 21.2 radians per second. And then for PC, which is only in the Y direction, I find negative 24.6 meters per second. Okay. And if I switch over, you got that's the right answer. It matches how the book did it. So the book, I mean, they kind of work it out a little differently. I mean, it's basically the same kind of thing, but just they do it a little differently. And they end up with the same velocity. And I don't see that they write down what they found for omega. Oh, there it is, 21.2. Yeah, okay, so it's the same. All right, and getting the negative velocity is crucially, getting it all to work together is crucially, to get the minus sign here, then you have to get the right minus sign on omega, but to get the right minus sign on omega, you have to get the right angles at the start. So that's why I say it really pays off to think about what you expect the answer to be. Are you expecting omegas to be positive? Are you expecting it to rotate clockwise or counterclockwise? And if you can figure that out, that will give you confidence in your answers.
So Sean, so like most of these like the problems that looks like this are like almost all the same. Like if I do like a lot of exercises of them, I might just like start to, you know.
I think it's the same.
Yeah.
Yeah.
But
the other little trick is that when things don't slide, like the wine bottle rolling, that one velocity was 0. Those are the 2 tricks.
all right.
The rest of it is this game.
Yeah. All right.
All right. I know some of you guys have to go, so if you need to go, head out. Shane, I can try to answer your question. We'll just add it. We'll keep.
Actually, that problem right there helped me out a lot because now it was like a little concept there I was missing, but I think I'm good now.
Okay. All right. So I will upload this video to YouTube. Okay.
All right. See you, Sean.
See you guys.